Chapter 3b, Analytical or exact solution of kinetic equations for diffusion limited systems. In the previous chapter 3a, I have introduced the semi-empirical solution of the same kinetic equations for diffusion limited systems. In this chapter, I'll give you more exact, and that is to say, analytical solution about the diffusion limited systems. We are still on the diffusion limited systems. As you know, diffusion limited systems could be described by Fick's law. We have two different Fick's law. Here is the first one, Fick's first law. Fick's first law is the equation to define current in diffusion limited systems. Mole flux of oxidized species or an electroactive species is equal to minus diffusivity of the electroactive species with the gradient of concentration of oxidized species. That is the Fick's first law. This symbol, pronounced as del, is the gradient operator, which is the first derivative operator. That is to say, gradient of scalar function f of xyz is equal to del f of xyz is going to the first derivative of function f with respect to x and y and z for the Cartesian coordinate systems. For cylindrical or spherical coordinate systems, the detailed description about the gradient operator is changed from this one to this one for cylindrical or this one for spherical coordinate systems. In this course, most of cases I will assume that only one-dimensional diffusion from the electrolyte to electrode surface or vice versa. So we will consider only one single x-axis. Therefore, this generalized equation is simplified into this second line. Mole flux of oxidized species is equal to minus diffusivity with the concentration of oxidized species dx. So that is the gradient of the concentration along x. Then at electrode surface, the surface concentration gradient of oxidized species would define the surface mole flux, and this surface mole flux is closely related to the current, which is equal to current per NFA. Therefore, it is the reason why I have said the Fick's first law is the equation to define current. I mean, the current is obtained from the surface concentration gradient. That is the meaning of Fick's first law. Here is the summary of 4 important points of Fick's first law. Again, Fick's first law defines the driving force of molar flux of electroactive species and resultantly current here. Here is the concentration gradient. From x to x plus del x. Your concentration increases from here to there. In this case, the concentration gradient direction goes from the left to the right. However, the electroactive species slide down from higher concentration to lower concentration. Therefore, the mole flux direction is going from the right to the left, which is opposed to the direction of concentration gradient. Those things are the second and third points. Let me read it. Diffusion is in the direction opposing the concentration gradient, I have said, from this picture. The third point is that electroactive species are expected to flow from higher to lower concentration. I have said about that. And the fourth point is concentration of electroactive species in the Fick's first law is the function of only x, where x is the distance from the electrode surface toward electrolyte. There are no information about time in the Fick's first law. There are no time here. Following the Fick's first law, here is Fick's second law. The Fick's second law is the partial differential equation, or PDE, for solving the problem of diffusion limited systems. For obtaining the analytical solutions, this Fick's second law is more important than the Fick's first law. As I have said, the Fick's first law is just the definition of current. However, from the Fick's second law, you could obtain the solution about the concentration profile. By using the concentration profile obtained the second law, you could get the values of current by using the Fick's first law. This is the Fick's second law. The concentration of oxidized species dt. Finally, we have found the time variable. In the first law, you cannot find the time variable. It's equal to diffusivity of oxidized species with Laplacian of the concentration of oxidized species. This del square is called Laplacian operator, which is the second derivative operator. For example, for Cartesian coordinate systems, the Laplacian operator of the scalar function f is going to the second derivative of function f with respect to x and y and z. Of course, according to cylindrical coordinates or spherical coordinates or some the other coordinate systems, then the detailed the operation is changing from the simple to more difficult or complicated ones. So here there are 2 points about the partial differential equations. The first one, concentration of electroactive species is the function of time. Finally, we got time variable as well as the distance. Therefore, temporal spatial information of concentration is obtained. In the case of one-dimensional diffusion, this generalized version of the Fick's second law is more simplified, like dc dt is equal to divisibility with d square c dx square. So I mean this is PD, and from the viewpoint of time you have the first order of PD, and from the viewpoint of x you should have the second derivative of the concentration. From this equation you will obtain the concentration profile along x with time variable. Right now we have two diffusion equations, Fick's first law and Fick's second law. What is the Fick's first law and Fick's second law? I mean, what is the meaning of those equations? The first law is the equation to obtain the current function. To calculate the current function, we need to have the concentration profiles. The concentration profiles could be obtained by using the Fick's second law. Anyway, we have those two equations. Then by using those two equations, we could solve the solution about the Chronoamperometry and Chronopotentiometry and voltammetry. Here is the first case, which is the Chronoamperometric responses. That is to say, current as a function of time. Here is the input for the chronoamperometry. Of course, at time equal to 0, I'd like to apply a fixed potential into the system. So, before time equal to 0, we would have no reactions. However, after we have applied a fixed potential, then some oxidized species is converted to reduced species as a result of reduction. Also, I'd like to assume that our applied potential is much more negative than the reduction potential of oxidized species involved in electrolyte. Then, the oxidized species is totally reduced into reduced species. Therefore, you cannot find any oxidized species on the surface of electrode. We could use the concentration of oxidized species at the surface of electrode is equal to 0 as the boundary condition of the Fick's second law. Anyway, our question is that, okay, so what kind of chronoamperometric responses could be obtained as a function of time? Let me start with the diffusion equation. This is the Fick's first law, and current would be obtained by the first derivative of the concentration at the surface of electrode. Therefore, we need to have the information about the concentration. The concentration profile could be obtained from the Fick's second law, as I said before. Here is the Fick's second law. dc dt is equal to diffusibility with the second derivative of the concentration with respect to x, or the distance from the electrode surface. We have assumed that the one-dimensional diffusion toward the electrode or out of the electrode. Only in that case you could simplify the Laplacian operator into just d square over dx square. This PD, partial differential equation, is the governing equation for the diffusion process of the mass limited system, mass transfer limited systems. This PD is the first order in terms of time and second order in terms of x. So we need to have a single initial condition and two boundary condition at x equal to infinity and at x equal to 0. What is the initial condition? I mean, what is the concentration at time equal to 0? Independent of location, you would find the bulk concentration, which is the value of concentration you have fixed or you have introduced just before your experiment starts, like 1 millimolarity of Fe3 plus. That is the initial condition. And the first boundary condition at x equal to infinity or in bulk electrolyte, the concentration is of course bulk concentration. Also, then let's go to the surface of electrode. At x equal to 0 or at the surface of electrode, what kind of concentration of oxidized species is found? I have said the concentration of oxidized species should be 0, independent of time, because we have an applied potential which is much more negative than the reduction potential of the reactions of interest. So all of oxidized species are reduced. You cannot find any oxidized species on the surface of electrode. So CO at x equal to 0 is going to 0. Okay, that's it. So right now we have completely defined our PDE systems. A governing equation, which is a partial differential equation with one single initial condition and two boundary conditions. Then you could find the solution. Or your friend could find the solution. Or you could use some software. Okay, here is the final solution about this Fick's second law. The relative concentration of oxidized species with respect to the bulk concentration could be described by error function of the ratio of x with respect to the thickness of Nernst diffusion layer. Can you remember the Nernst diffusion layer? In the previous chapter, we have used the Nernst diffusion layer. Delta as a function of time is equal to E root square of the product of diffusivity with time. So the thickness of the Nernst diffusion layer is changing with time. Anyway, let's go back to the concentration profile. We have the concentration profile, which is the function of x and also time. Let me think about the shape of this concentration profile. Also, what is the error function? Error function of x is equal to 1 over root square of pi with the integration of exponential function of minus t square with respect to time, with respect to t from minus x to x. Anyway, more important thing is its shape. So let me focus on the first quadrant of this graph. X equal to 0 to some positive value which have the physically meaningful range. In this first quadrant, you can find at x equal to 0, you don't have any concentration of oxidized species. This comes from the second boundary condition. And then concentration is increasing as x increases. Then finally, the concentration is saturated at the bulk concentration. That is the loaf shape of the concentration profile at time at a certain specific time. And then let me compare the concentration profiles at several different time scales. X is the distance from the electrode surface, and Y is the relative concentration, which is the concentration per the bulk concentration. Of course, the maximum value of this relative concentration should be 0, should be 1. At time equal to 0, at any x values, you should find just 1 values for the relative concentration, even at x equal to 0. However, just after we have applied a fixed potential into the system, the concentration at the surface is going from 1 to 0 suddenly, abruptly. In this case, time is equal to 10 to the minus 3 seconds. This point should be fixed at 0 after you have applied a potential. Therefore, the very steep concentration gradient is developed, and the slope of this concentration profile is directly related to the current. So at the initial period, you would have very high values of current, like that. In this picture, you can find time as x-axis, and y-axis is the diffusion current. So very high values of current is obtained at initial period of time. As time goes by, the concentration profiles or the gradient concentration, the gradient of concentration or concentration gradient would decrease as time goes by. Therefore, current is decreasing with time. The most important thing is that at any time we could find the common thing. The surface concentration should be 0, which comes from the second boundary conditions. So anyway, right now we have an analytical solution of concentration profile as a function of x and as a function of time. So let me put this concentration function into the Fick's first law. Then after the first derivative of this concentration profile at x equal to 0, then finally we could obtain the diffusion current for the diffusion limited system when you have applied a fixed potential. So this current is the function of time, is inversely proportional to the time. Let me read the equation. NFA, the root square of diffusivity of oxidized species with just bulk concentration per the root square of the product of pi and time. What is that? That is the Cottrell equation you have met in the previous chapter. So finally we obtain the Cottrell equation after solving the problems by using the Fick's second law. Okay, again back to Cottrell equation here, and let me check what kind of assumptions are hidden for obtaining the Cottrell equation. You should recognize that the Cottrell equation is obtained for the system of one-dimensional diffusion along x-axis toward or out of planar electrodes of infinite dimension along y and z axis. So please imagine the big plate of electrode the y dimension or z dimension of the plate electrode would be very large than the scale of the um, thickness of non-steady diffusion layer. So maybe those scales would be around several millimeter, at least the larger than 100 micrometer. Also, we have used the planar electrode as a geometry of electrode. When those the requirements are satisfied, then we could obtain the Cottrell equation. At the steady state, or when the time is going to infinity, the current or the steady state current would approach zero for the Cottrell equation, or for the one-dimensional diffusion along x-axis. Okay, that is the Cottrell equation. Let me change the situation. Still, we have the planar electrode from here to there, but the dimension of y and z are reduced from very large scale to very small scale, less than 5 micrometer. So just imagine some planar electrode. This area is the conductive materials, and out of this electrode you would have some insulating material. So in this case you could find some distorted current distribution around the boundary, which is contrasted the situation of the first case. In the first case of ideal Cottrell equation, all current is parallel to each other. There are no distortion. However, when you reduce the size of the planar electrode into the planar disk electrode, less than 25 micrometer, you could find some distorted current distribution around the boundary. In that case, you cannot use very simple Cartesian coordinate systems for Laplacian operation. You should use cylindrical coordinate systems for Laplacian for the fixed second law. dCdt is equal to diffusibility with the Laplacian. Looks a little bit more complicated than the one-dimensional Cartesian coordinate operation. In that case, we could obtain very complicated diffusion current equations, much more complicated than Cottrell equation. Even if I didn't show the complicated equation here. So let me check the steady state current for this a planar disk ultramicro electrode. The current at steady state should be zero at Cottrell equation, or for the large size planar electrode systems. However, in the case of the planar disk ultramicro electrode, the steady state current is going to approach a certain value, not zero. And the steady state current is proportional to the size of the disk electrode and bulk concentration with diffusivity. So this is the big difference between the large disk electrode and the small disk electrode. Also, let me change the geometry of the electrode from planar, very simple planar, into spherical electrode, like that. Of course, you could find the still distorted current distribution along the curvature of the spherical electrode. Then in that case, you should use these spherical coordinate systems for solving the Fick's second law. And here is the result. Diffusion current as a function of time is equal to some first term plus the second term. The first term is exactly same as the Cottrell equation. Let me check it. NFA CO star per pi DO root square of DO and root square of time. So this first term is going to Cottrell equation. But you could find one more term. Here is 1 over R0 with the NFA dN bulk concentration. This is the correction term for the spherical electrode. So the diffusion current for spherical electrode consists of Cottrell equation plus spherical correction term. At a steady state, of course, the first term is going to 0 and the second term is going to a certain value, like this one. This the steady state current value, well, current equation is very similar to the case of case of the ultramicro electrode of disc shape. So the diffusion current of spherical electrode is proportional to the size of sphere electrode with diffusivity and concentration. You have derived the diffusion current equations when we have applied a very big overpotential into the system. For example, for the reduction, we have applied the very negative potential when compared with the former potential. In that case, we have obtained the Cottrell equation and we have obtained the Cottrell equation plus some spherical corrections depending on the geometry of electrode. So in this slide, I'd like to extend the equation for the large overpotential into equation for the small overpotential. Here is two groups of equations, and the first group of equations include the equations we have just derived. This one is Cottrell equation, which is obtained for the planar macro electrode when you have applied a very large overpotential value into your system. For the reduction, E apply is much more negative than the former potential. Or for oxidation, your applied potential is much more positive than the former potential. At the surface, you cannot find the oxidized species for the reduction, or you cannot find the reduced species for oxidation. So you have Cottrell equation for the planar macro electrode, or for the spherical electrode, you have some spherical correction. Then let's go to the second group for the small overpotential values. Let me say my applied potential is around the former potential or equilibrium potential or standard reduction potential. Then in this situation, you would have the surface concentration composition, which is determined by the Nernst equation, right? Because we are still thinking about the reversible reaction in the mass transfer limited system. So let me define the composition of the oxidized species and reduced species as zeta. Actually, zeta is like that. The concentration of oxidized species per concentration of reduced species. Of course, the ratio is determined by your applied potential. Then, what is the main difference between the first group and the second group, or the large potential case, overpotential case, and small overpotential case? The only thing we can recognize is that 1 plus zeta term. Okay, here quadratication, and in the second group, quadratication divided by 1 plus zeta. And here, this is the first group equation for the spherical. Then in the second group, you could find also 1 plus zeta in the denominator. So I could say the second group current, or the current at small overpotential, is equal to the current at large overpotential divided by 1 plus zeta. Let me think about the value of zeta. If you applied very negative potential into your system when compared with the former potential, then what does it mean? It means oxidized species is more converted to reduced species. So the composition of oxidized species to reduced species is going to 0. Then in that case, the second group of the equation is turning back to the first group of the equations, which is the case at large overpotential. So I could say the second group equations are more generalized version of the diffusion current equations. Let me think about what happens when we apply the potential at former potential. Then this term is going to 0, so zeta is going to 0. I means the concentration of oxidized species is equal to the concentration of reduced species at former potential. In that case, I2, I means I at former potential is equal to the current at large overpotential per 2. So I mean just 50% of current is obtained when you have applied the former potential into the system. Here is the curves about that, and current versus time curve, and the black line is indicated by the diffusion current at very negative overpotential. However, at the former potential, the current would follow this red line. Of course, the red line is just 50% of the blank line. I mean, at the former potential, zeta is going to 1, and 50% of the first group is going to the second group. Here is the second case, which is the chronopotentiometric responses. In this case, we will apply a fixed current instead of a fixed potential. Then we'll try to find the potential as a function of time. You know, we are still on the diffusion limited system, and only different thing is the input. Everything is not changed except of the input signal. So governing PDE equation is still Fick's second law, the same thing, which was shown in the first case of Chronoamperometric responses. How about the initial condition? At time equal to 0, you should find the bulk concentration independent of location, the same, shown in the previous chronoamperometric responses. How about the first boundary condition? In the bulk region of electrolyte, the concentration should be the bulk concentration, the same. Only different thing between chronopotentiometric and chronoamperometric responses is the second boundary condition. In the chronoamperometric responses, I have said we should have the zero concentration of oxidized species because we have applied a very large negative potential into the system. Every oxidized species is totally converted to the reduced species. However, in this chronopotentiometric experiment, we have controlled the current. So, the fixed current indicates the fixed concentration gradient at the surface. We didn't fix the surface concentration. We have fixed the surface concentration gradient instead of just concentration. So the second boundary condition is that current, it is a kind of a value like 1 milliampere, is equal to NFA diffusivity with the surface concentration gradient. That's it. Again, only different thing between chronopotentiometric and chronoamperometric systems is the secondary boundary conditions. Okay, right now we have everything we need to require for solving the problem. So here is the resultant solution about these PD systems. Concentration is equal to bulk concentration minus something. And in this second grand term, you could find some time variable and the location or x variables. By using this equation, I have plotted several concentration profiles at the various different time scales. At time equal to 0, of course, you should find the only bulk concentration at any locations like that. Just after we have applied a fixed current into the system, the concentration gradient is developed. As time goes by, similar thing is developed like that. The invariant thing and the most important thing is that the surface concentration gradient should be the same. I mean, the slopes of the concentration profiles should be the same, even if the time goes by. Let me draw the slope here. And here is the slope, another slope, another slope, and another slope. When the surface concentration is going to 0, we didn't experience any change in the slope of the concentration profiles. This is the characteristic thing of the chronopotentiometric responses. So, okay, so can you remember the concentration profiles for the chronoamperometric responses? In that cases, the surface concentration was fixed at 0. Of course, the concentration gradient was changed with time in the previous chronoamperometric responses. However, the slope or concentration gradient were fixed, independent of time. It is most important point of chronoamperometric responses. Okay, so let's go back to the concentration profile equation, and at x equal to 0, the x term is going away. Then you this is going away and this is going to 1, so you would have obtained this equation. Then let me assume that at time equal to tau, the surface concentration is going to 0, because at tau every molecule should be consumed. So this equation is going to the final equation, which is so-called Sand equation. This Sand equation is very similar to the Cottrell equation in terms of the shape or formulation. Here is you can find the root square of time term. Actually, that is not just time. This is the time which can be used as a measure of the amount of oxidized species. So, or transition time or reaction time. Anyway, here, and also current is here. So I mean the current is inversely proportional to the root square of time scale. That is the Sand equation, which was obtained for the planar macro scale electrode. And the shape of the potential profile looks like that. Please think about the concentration profiles. That is the most important thing, which should be compared with the chronoamperometric cases. You have solved the diffusion problems for obtaining the equations for chronoamperometry and chronopotentiometry. What you derived is the Cottrell equation and Sand equation. You have used two equations and Fick's first law and Fick's second law. By using the Fick's second law with appropriate initial conditions and boundary conditions, the first thing you have obtained was the concentration profiles. And then by taking the first derivative of the concentration profile at the electrode of surface via Fick's first law, then you have obtained the current function for the chronoamperometry and also chronopotentiometry. In this subchapter 3, we'll get the description about the voltammetric responses. That is to say, current as a function of potential by using the same method based on Fick's first and second law. The Faradaic reaction we will focus on. Of course, ox plus an electron is going to reduce the species. We will see the potential for the forward scan and also backward scan. Forward scan to negative direction can be described by this equation. So the starting point is the initial potential E sub I, and then it is going up to the direction of the negative potential. The scan rate is lambda. The scan rate is V, and then at the end of the forward scan, you would obtain the potential value at E sub I minus scan rate by lambda. Lambda is the end time of the forward scan. At the lambda, then we will invert the scan direction to the positive potential. So the backward scan to positive direction can be described by this equation. The first point was EI minus scan rate with lambda time plus then going down toward the positive direction. So scan rate with t minus lambda. That is the equations for the operational condition of potential sweep. Then let's go to the governing equation or partial differential equation to describe our systems. Of course, The governing equation is the diffusion equation based on the Fick's second law. dCdt for the oxidized species is equal to the product of diffusivity with the second derivative of the concentration of oxidized species. In this case, I'd like to give you one more diffusion equation for the reduced species. Everything is the same, but this is for the reduced species instead of oxidized species. So right now we have two PDE, and the first order for the time variable and the second order for the location variable. So we need to have two initial conditions and four boundary conditions. Let me start with the initial condition. At time equal to 0, independent of the location, the concentration of oxidized species and reduced species should be the initial value of those species, or bulk concentration of those species. So, concentration of oxidized species at time equal to 0, independent of location, should be its bulk concentration. Also, the concentration of reduced species should be also bulk concentration. Let me assume that I have introduced only oxidized species into electrolyte without any reduced species. For example, CO star, star means bulk. CO star is 1 millimolarity of Fe3 plus, and Cr star for reduced species is 0 millimolarity of Fe2 plus. So Cr is going to 0. Then let's go to the boundary condition number 1. In the bulk region of electrolyte, of course, all of concentration, the concentration of all species should be equal to the bulk concentration or initial concentration. So CO is going to bulk and Cr is going to bulk, which is equal to 0. And then let me go to the boundary condition number 2. At the interface between the electrode and electrolyte. So x equal to 0. And the first one of the boundary condition 2 is obtained from the steady state condition. The consumption rate of oxidized species should be the same as the generation rate of reduced species, of course. One oxidized species is consumed means one more of reduced species is generated. So minus dCdt for oxidized species is equal to plus dCdt for reduced species. It means the summation of dCdt should be 0. So dCdt for ox, dCdt for reduced should be 0. And each term is going to the second derivative of concentration for the location x. This conversion is based on the Fick's second law. So this one plus that one is equal to 0. This is the first one of boundary condition number 2. And then one more boundary condition is required at the interface between electrode and electrolyte. This boundary condition, or the last boundary condition we need to have, would be determined by the charge transfer kinetics relative to the diffusion rate. So let me think about the reversible cases. Actually, you are still on the mass transfer limited or diffusion limited systems. It means your charge transfer kinetics is really fast. Reversible. So in that case, the fourth boundary condition at x equal to 0 is Nernst equation. The surface composition of oxidized species to reduced species is determined by your applied potential. Actually, this is the Nernst equation, right? And then right now we have everything. 2 initial conditions, 4 boundary conditions for 2 governing equation based on fixed second law for oxidized species and reduced species. Then, therefore, you could solve the problems. Maybe you could use software, or you could believe your hands. Anything is okay. Then anyway, concentration profiles as a function of time and x could be obtained from the fixed second law. Then it's time to use the fixed first law. Fixed first law is saying that the current is obtained by the first derivative of the concentration profile at x equal to 0. Right now we know the information about the concentration, so we could obtain the final solution, the current function. Here is the current function as the final solution. This current function is the function of potential, and which can be split into 2 terms. The first term from here to there is potential independent term, and the second term is potential dependent, and which is called chi function. Let me check the first term, which is the potential independent. This first term is the combination of several parameters and number of electron transferred, Faraday constant, and electrode area with bulk concentration of oxidized species, and something inside of the root square. What is that? Pi, just constant, diffusivity of oxidized species. And the other thing is sigma. Sigma is a kind of scan rate. Here is the definition. Sigma is proportional to the scan rate, and this scan rate is normalized by RT per NF. So let me check the unit. The unit of scan rate is millivolt per second, and RT per NF is millivolt. So NF per RT is going to 1 per millivolt, the product of those 2 units, which is going to the per second. So the unit of sigma is per second, and I'd like to interpret this sigma as the potential normalized scan rate. So again, sigma is NFRT per scan rate. Anyway, in the first term, you can find various parameters, and some of them is just constant, and some of them is fixed, like temperature, usually 25 Celsius degree, and scan rate, you will fix it for your own experiments. So we have this kind of term is involved in the current function. And then let's go to the second term, the potential dependent chi function. It is called chi, chi, chi. And this chi function is the function of the potential. It means at a specific value of the potential, this chi gives us some constant value. So it means at a specific potential, current is proportional to those parameters with some constant. Okay? Then let me define this chi function as the dimensionless current function. So again, chi function as a function of potential is equal to real current value per NFA CO star with pi diffusivity sigma root square. This was the first potential independent term. Anyway, let's go back to the original equation. Again, current is proportional to those parameters with some constant value at a specified potential value. Okay, so let me think about the shape of this chi function, because the current function is proportional to the chi function with some values of parameters. So the shape is determined by this potential dependent function. This is chi function curve, and x-axis is the n number of electron transfer with the potential difference between your applied potential minus the average peak potential. E with subscript a half is the average values of the cathodic process and anodic process of peak potential. Y-axis is the chi function, and actually in this curve I have multiplied the root square of pi in front of the chi function. Then let me follow this curve. This is the famous duck shape, so resultantly we have a duck shaped cyclic voltammograms. Let me check several characteristic points. Here is a peak. Of course, the potential at this peak is called peak potential. In this case, maybe cathodic peak potential. And the current at this peak potential is called peak current. Let me think about the peak current first. Right now, the peak potential is fixed around here. It means the peak current is proportional to the first term. I mean the first term, which is the potential independent, right? And chi value is going to some constant at this specific potential value. So let me check the parameters involved in the first potential independent term, n, f, a, co star, blah, blah, blah. So let me check it. Co star comes from here, and the root square of scan rate from the sigma value. Sigma have just scan rate, so sigma root square means the root square of scan rate right here. And then diffusivity here, the root square of diffusivity, A, the electrode area here. And how about number of electron transfer? Here is just n. And also sigma has a n here, so n by the root square of n from sigma is going to n to the 3 over 2. So right now we have the equation for the peak current, which is proportional to the n to the 3 over 2 with a, the root square of diffusivity, the root square of scan rate, and bulk concentration with some constant value. What's that? This is the Landry-Sevcik equation. From the Landry-Sevcik equation, we have recognized that the peak current is proportional to the root square of the scan rate. So if your peak current is following very well with this relationship, then you could say your charge transfer reaction or Faraday reaction is reversible, or its kinetics is really fast. The other thing is the peak to peak gap. I mean peak to peak potential gap. From this chi function, what we know is that the difference between peak potential and the average potential of peak potential is 28.5 per n millivolt at 25 Celsius degree. It means peak to peak gap is 2 times of this value. That is to say 57 per n millivolt at 25 Celsius degree. So you have got an cyclic voltammogram, and you have observed that the peak-to-peak gap of your electrochemistry is 57 millivolt with 1 electron transfer. Then you could say my electrochemistry is really reversible or facile or fast or non-stop. So again, let me emphasize 2 points. Peak current which is proportional to the root square of scan rate, and peak-to-peak gap, it should be 57 millivolt for 1 electron transfer electrochemistry if you have a reversible electrochemical process. Okay, let me think about the scan rate effect. Overall current is split into Faraday current plus non-Faraday or capacitive current. And the Faraday current is proportional to the root square of scan rate. However, the capacitive or non-Faraday current is proportional to just the scan rate. So that is to say, or therefore, as the scan rate increases, the contribution of the capacitive current to the overall current increases because the IC capacitive current is proportional to the scan rate to the 1. However, Faraday current follows the root square. I'd like to emphasize the root square of the scan rate. So at high scan rate, then the contribution of the capacitive current is going up. Therefore, if you want to focus on the Faraday current, it is better to sweep potential at a slower scan rate. So I means it is better to use slow or low scan rate for checking the Faraday reactions. Here's some representative example. Let me start from here. Very slow scan rate like 1 millivolt per second. And in this case, let me assume that 1 milliampere Faraday process or Faraday current is observed while just 0.1 milliampere capacitive current is measured. Usually, the non-Faraday current is much smaller than the Faraday current. And then let me increase the scan rate into scan rate from 1 millivolt per second to 9 millivolt per second. It means 9 times, well, 9x. So 0.1 by 9 is going to 0.9 milliampere. However, 1 milliampere by root square of 9 is going to 3 milliampere. So at 9 millivolt per second, we cannot neglect the capacitive current. Even if at 1 millivolt per second in the previous example, we probably neglect the contribution of the capacitive current. Let's go to the third example. Then right now 100x, I means I have increased the scan rate from 1 millivolt per second to 100 millivolt per second. It means 100x. So 0.1x 100 times. So 10 milliampere. However, 1 milliampere by the root square of 100x is going to 10 milliampere. It means the Faradaic process and non-Faradaic process are competitive to each other. So half to half. And moreover, I have increased 900 millivolt per second. It means 900x. So 0.1 is going to 90 because 0.1 by 900 is going to 90. However, 1 by root square of 900 is going to 30 milliampere. So it means at such a very high scan rate, my Faraday current is became smaller than the capacitive current. So the high scan rate experiment is not good for investigating the Faraday reactions. So again back, if you want to focus on the Faraday current, it is better to sweep potential at a slower scan rate. Okay, until now we have focused on the reversible Faraday reactions. So from the reversible Faradaic reactions, we have used the Nernst-Chen equation as the force boundary condition at the interface between electrode and electrolyte. And then we have obtained the current function, which consists of two terms. One is the potential independent term, and the other is potential dependent chi function. Then how about the quasi-reversible or irreversible reactions? For the quasi-reversible reactions, or if you have a slower charge transfer Faradaic reactions relative to the diffusion the rate, then you cannot use the Nernst-Chen equations for the force boundary condition. Instead of Nernst-Chen equations, the current at the interface is defined by the forward reaction rate of the concentration of reactants minus backward reaction rate with the product concentration. This is the mass action law, which is always used for the chemical reaction equations, while the kinetics of chemical reaction equations. Okay, so after changing the force boundary condition from Nernst-Chen equation to some kinetic description, then we could obtain the final solution about the quasi-reversible systems. Actually, the rough sketch about the final solution about quasi-reversible is very similar to the situation of the reversible reactions. Let me check it. Here is the current function, of course, as the function of the potential is split into two terms. The first term is the potential independent term, which is exactly equal to the potential independent term of the reversible case. This one is the same as this one. And then let's go to the second term, which should be the potential dependent. I have used the character chi for the reversible systems. However, for the quasi-reversible systems, I'd like to use the psi as the name of the function, because the function is different to each other. This capital psi function is the function of potential, like in the reversible systems. However, you should recognize one more thing. Here is the lambda as the parameter to define the quasi-reversible system. What is the meaning of lambda? Lambda is the ratio of charge transfer rate versus mass transfer rate or scan rate. So by the definition, lambda is So lambda is defined as the ratio of charge transfer versus mass transfer. So the charge transfer rate is represented by the standard rate constant, which is the reaction rate, a kind of reaction rate constant. And the other thing is diffusivity. Alpha is usually assumed to be 0.5, and root square of the product of diffusivity of oxidized species and reduced species here. So this represents for the mass transfer rate. The other thing is the scan rate. Scan rate here, actually potential normalized scan rate here. So what does it mean? The psi function is determined by the value of lambda. What is the meaning of large value of lambda? Large value of lambda, for example, larger than 15, then it means charge transfer is much faster than the mass transfer or scan rate. So it means my electrochemistry is reversible. So reversible system. It means the overall kinetics is determined by the mass transfer or scan rate. So higher values of lambda indicate reversibility. Very reversible. Let me go to the other extreme. If the value of lambda is very small, means your charge transfer is very slower than the mass transfer or scan rate. So this system can be considered as the totally irreversible. So between those two values, like 15 to about 10 to the minus 3, then we call the in between situation as the quasi-reversible. Let me think about what kind of graphs can be obtained from this psi function with lambda value. Let me check the voltammograms here. And I have borrowed the same equations from the previous slide. Here is the current function. That is the first term of which is the potential independent, and the second term which is the potential dependent term. And here's the lambda. Lambda was defined by the charge transfer and mass transfer. Sometimes instead of just lambda, we are using the small psi. It is not the capital psi. This is the small psi, which is equal to lambda per the root square of pi. Actually, small psi, lambda has the same meaning. The ratio of the charge transfer versus mass transfer. So here is the psi function. Y-axis is the psi function value or current value, and x-axis is the potential. So let me focus on the middle curve here. And the dashed line is obtained from the reversible systems. Actually, I could say chi function we have derived in previous slide. And the other solid lines is obtained by the psi function with 4 different values of lambda. Lambda 10, 1, 0.1, 0.001. As the lambda value is going down, that is to say, as the irreversibility is going up, then the peak current is going down, with the peak-to-peak potential gap is increasing. This is two characteristics as the irreversibility is involved in your systems. Again, if you have met some irreversibility, you could expect lower peak current and larger peak-to-peak gap, peak-to-peak potential gap when compared with the reversible system. Okay, let me check the peak current behaviors. X-axis is the lambda, and from the left to the right, the lambda decreases from 100 to 10 to the minus 4 or something like that. Y-axis is the ratio of the peak current versus peak current of reversible systems. At high values of lambda, like larger than about 15, then the value of the ratio of peak current is almost 1. It means reversible. However, when the values of lambda is going down from about 10 to 0.1, you could observe the current ratio decreases along the lambda values decreasing. For example, let me think about the curve obtained at alpha is 0.5, and then at the very first time the current ratio was 1 or 100%, but it is decreasing into about 80% of the initial values. Then after a specific values, after after the specific values, like in this case 0.1 or something, then the current ratio is saturated about 80% for the case of alpha equal to 0.5. So what we obtained from these curves that the peak current would decrease as the irreversibility increases. It is a very important point. Okay, so I'd like to explain about the Nicholson's method, which is developed at 1965. By using the Nicholson method, we could calculate the standard rate constant, which is a measure of the kinetics of charge transfer of Faradaic process. From the lesson of the previous slide, we know that the peak current is going down. Also, more importantly, peak-to-peak gap increases as the irreversibility goes up, right? So, let me check the text. The largest peak current and the smallest peak-to-peak gap are obtained from the reversible systems, because the charge transfer is very facile enough not to hinder the mass transfer. The next question is that what if the charge transfer is slow enough to affect the mass transfer? So, of course, the decrease in peak current and the increase in peak-to-peak gap are expected. Larger peak-to-peak gap would indicate slow kinetics. Then, can we obtain the values of the standard rate constant K0 like that? Yes, Nicholson method is the answer. So let me check the equations about the quasi-reversible reactions. Here is the current function for the quasi-reversible process, and this is the potential independent term, and the other thing is potential dependent term psi, and psi is the function of potential with the lambda as the parameter, and lambda is the ratio of the charge transfer to mass transfer. So lambda is fixed, then psi, the shape of psi function is fixed, then the delta EP, peak-to-peak gap, is fixed. Based on this kind of lessons, then we could expect some method to measure the K0 or standard rate constant. So let's go follow the backward direction of this flow. Delta EP, peak-to-peak gap, is obtained from the experimental data. Then from this value of the peak-to-peak gap, we could expect the psi function or large psi function. And then it means lambda is determined, or small psi is determined. I have said sometimes small psi is used instead of the lambda. Actually, psi is simply just pi minus 1 over 2 with lambda. Anyway, lambda or psi, small psi, is determined. Then by using this equation, and also after I obtain some information about the diffusivity of oxidized and reduced species, with the assumption that the alpha is equal to 0.5, also we have fixed the scan rate at like 100 millivolts per second, then we could calculate the standard rate constant from the values of small psi or lambda. It means if you know the value, the peak-to-peak gap from your cyclic voltammograms, then you could calculate the K0 value. Great, interesting. So I'd like to give you some example. We are still on the Nicholson's method, and then I'd like to give you an example. Step 1. Obtain cyclic voltammograms. So we have several cyclic voltammograms, and I'd like to focus on this kind of very good looking duck here, dashed line. And then read delta EP. It means peak-to-peak gap. So this is anodic process and cathodic process. Peak-to-peak gap is 70 millivolt. Right now we have, and we are investigating about an electroactive species, which is the ABTS here. This is the one electron transfer electrochemistry. Let's go to the second step. Find the value of small psi corresponding to the value of delta EP in the table of small psi and delta EP here. This table is made by Nicholson at 1965, or by using the psi functions, capital psi functions, you could calculate it. Anyway, right now we have 70 millivolt for the delta EP, and N value is 1 electron transfer. So 70 millivolt for this column, and you can find 70 millivolt between 68 and 72. So you need to do some interpolation between those two values. For the 70 millivolt, then the small psi is expected to be about 2.45. And then let's go to the step 3. Calculate the value of K0 from small psi by its definition. Definition is here. So what we know is that the small psi value 2.45 here, and K0, this is unknown, and actually that is our target we want to calculate. And pi constant, the oxidized species and the reduced species is here for the electroactive species, which is about 3.22 by 10 to the minus 6 centimeters square per second. So put there, and let me assume that alpha is 0.5 there, and F constant, R constant, T is 25 Celsius degree, about 300 Kelvin, and scan rate, you should know that because you did experiment. So here 100 millivolts per second. So right now we have filled out every parameters with some values except of K0. So because we know the value about small psi, which is the 2.45, you could calculate the value of the standard rate constant. K0 is equal to 0.0154 centimeter per second. So the Nicholson method can be widely used for the measuring the standard rate constant. So the basics behind the Nicholson method is the comparison between the reversible reactions and quasi-reversible reactions. If you find some deviation from the ideal cases, then you could measure or estimate the degree of irreversibility, which is the value of the standard rate constant.